after beginning the course with basics of probability and some important tools, first moment method, second moment method, generating functions. Today we're going to begin the topic of the rest of the course, which is Markov chains. So first, what is a stochastic process or a random process? We've seen random variables, we've seen some stochastic processes, but formally, what's a random process? So it's a collection of random variables, sometimes people say a family of random variables, indexed by some set T. And so usually we'll think of T as a sequence of steps, step 0, step 1, step 2, or we can think of T as half line. In that case, we would say our process evolves in continuous time. So what are some examples? Two main examples. The simple random walk, S0, S1, S2, and then the Galton-Watson branching process, where Zn is the number of individuals alive at step n. So again, this evolves in discrete time, in a sequence of steps. So this is a stochastic process. So there's all sorts of ways to collect random variables on the same probability space. One way would be to make these random variables independent, but that's not what we're interested in. We're interested in how the random variables evolve together. So notice simple random walk, Galton-Watson process. In both cases, the random variables in the collection are not independent of each other. Now we'll define a Markov process or a Markov chain. Here's the definition. The probability that xn takes a value s conditioned on its entire history up to that point. x0 takes some value, x1 takes some value, all the way up to xn minus 1 takes some value. This should equal the probability that xn takes that same value s, just conditioned on the previous value. So the condition on xn minus 1 equals little xn minus 1. And this should hold for all choices of s, x0, x1, up to xn minus 1. Another way to say this, and you can check to see that this makes sense, is that in a Markov chain conditioned on the present value, the past and future should be independent. Okay, and a special case of a Markov chain, and this is what we'll study most. Markov chain is time homogeneous if the probability that xn takes a value s, given that xn minus 1 is q, is the same as the probability x1 equals s, given that x0 equals q. So the idea is that the step doesn't play into the distribution. So simple random walk satisfies this. If you know that the current value is 10, then you have 50-50 chance to go to 11 or 9. That doesn't depend on what step you're at in the process. Again, branching process is also time homogeneous. If you know that there's 100 individuals at the current step, you know what the distribution at the next step will be. It doesn't matter in what generation you are. Okay, so now let's give some notation. So, and this is for a time homogeneous Markov chain. So now we can say that the probability that xn equals j, given that the previous step was I, we can just call this pij, since this does not depend on n. Right, this also equals probability that x1 equals j, given that x0 equals I. Okay, and then we can think of forming a matrix with the pij's. So here we have a matrix, this is P, and the ijth entry, so this is P11, P21, P12, Pij. So this is the transition matrix of a time homogeneous Markov chain. Notice that these matrices can have countable dimension, so the simple random walk, the branching process, it isn't a finite matrix. There's countable number of rows, countable number of columns. But the rows and columns are both indexed by the state space. So we can write S size of the state space by size of the state space for this matrix P. Okay, how can we represent a Markov chain? This is another, besides the transition matrix, we could also sort of draw a diagram. We can have nodes for the different states, and then directed arrows for possible transitions. Okay, so this represents a Markov chain, and now we need to assign probabilities. So let's say this is state 1, state 2, this would be P1, 2. Let's say this is state 3, state 4, P1, 3, P1, 4. Now, this is the probability that starting at state 1, you go to state 2, starting at state 1, you go to state 3, starting at state 1, you go to state 4. What should we have? We should have sum over all possible destinations, Pij, Pi, Pik should equal 1 for all I. And this is the same as saying that in the transition matrix, the row sums should equal 1. And now we come to another fact about Markov chains. So here the notation is Pij of n, comma, n plus m plus r. This is the probability that, let's see, this is the probability that x n plus m plus r equals j, given that x n equals I. All right, so Pij from before was just Pij of 0, 1, or Pij of n plus 1. Okay, so the Chapman-Kolmogorov equations say that the probability of going from state I to state j and m plus r steps from step n is the probability from summing over all possible intermediary states k, the probability to go from I to k in m steps, times the probability to go from k to j in an additional r steps. Okay. Now let's introduce a little bit more notation. Pn, this is the matrix whose entries are Pij of n steps. So this is the n step transition matrix. So Pm plus r of Ij, this is the probability to go from I to j in m plus r steps. Here again, this is time homogeneous case. What the Chapman-Kolmogorov equations say in this case is exactly Pm plus r of Ij equals the sum over all intermediary states, and then the ikth entry times the kjth entry of the m and r step transition matrix, respectively. And this should look familiar, perhaps. This is actually matrix multiplication. So what does this say? This says that the n-step transition matrix is the one-step transition matrix raised to the nth power.